Uh, okay, so thank you very much. Yeah, so my name is Rodrigo Pena. I'm currently a postdoc at the Biodynamics Lab at Horacio Houston at New Jersey Institute of Technology. And I'll be discussing this work that we have been developing and revealing the link between spiking cross-correlation patterns and underlying subthreshold neuronal dynamics. So essentially, cross-correlation functions are very useful in the context of neuroscience. So you imagine, for example, that we can take the so-called spike trains from neurons. For example, if you have a neuron with a spike train and x of t and another one y of t, we can get some pretty useful information from how those neurons are related by evaluating their cross-correlation functions. So you can, for example, infer connectivity. You can get some information about the synaptic properties of those connectivities. But ideally, those neurons, they have some intrinsic dynamics, and it is understandable that intrinsic dynamics should play a role on the spike trains of the neurons individually, and this should be somehow reflected on the cross-correlation function as well. So here I have some experimental examples and also computational examples of common cross-correlation functions. And for example, in this particular case, where we have a monosynaptic connection, which means that a neuron is sending a synapse in one direction to another neuron, we see a very nice cross-correlation peak, which we can use to infer and say that these neurons are connected. So there is a sharp peak within a few milliseconds in the cross-correlation function. So this is a special case, but we might see that, for example, when connections are very strong. But it's very useful to get information. It's very informative if you have a large data set and you want to infer this connectivity. But also, for example, if you want to see the synaptic properties, like if the connection is excitatory or inhibitory or timescales of the synapses, you can get that information. Nevertheless, there is somehow a lack in the literature about how the intrinsic dynamics of the neurons. So the neurons themselves, they have some intrinsic dynamics that comes from ion channels, for example. And our question arises from this fact. So how, whether and how the intrinsic dynamics of neurons can play a role on cross correlations like this. So, and if so, it is understandable that we need to have this knowledge when we try to infer connectivity, for example. To evaluate such a problem, we rely on computational models of pairs of neurons. So we have been using this model called ultra-precise monosynaptic model from Platievic's. And in this type of model, we run two neurons over many trials. So we have a presynaptic neuron and a postsynaptic neuron. They are receiving noise input, but in every trial, we inject the same amount of action potentials, kappa, from the presynaptic neuron into the postsynaptic neuron. So irrespectively of the trial, the amount of synapses that for the postsynaptic neuron will receive, it's the same. And then we can evaluate autocorrelation functions and cross-correlation functions from those neurons. So, so we will have pictures like this, where we see autocorrelation functions and cross-correlation functions, and you can see here the very same feature that we would expect from those experiments that I showed you before. So there is a sharp peak within a few milliseconds in the cross-correlation function, which comes from the fact that those neurons are connected, and that, since I know that because this is a simulation. But the question lies on the fact that those neurons, they have some nonlinearity embedded in their equations, like an FFV, and how is it that this cross-correlation function will reflect this nonlinearity? And if I change that, what are the features that I'm going to observe? So let me start with a simple example of an integrated fired neural model. So in this case, we just have minus v, so it's a pretty simple case, but even here we observe the sharp peak in the cross-correlation function. And there isn't much to say about this case, because even if you play with the parameters of such a model, like the EL, which is the reversal liquid potential, or GL, the conductance, you can shift those nuclines, which are placed here in green, and you go closer to the threshold or closer to the reset, which are in red here, or you can play with the angle of such nuclines, which will influence the dynamics of such a neuron, but you cannot really qualitatively change the sharp peak that you observe in the cross-correlation function. You can, what you can do is to change the peak amplitude, like you increase or decrease with EL or GL, but it's only a meaning that more spikes are being transmitted, not so much, not that there is a very interesting feature showing up. However, when we start to introduce some nonlinearities, as for example in the ADEX model, the adaptive exponential integrated fired neural model, so here the f of v is an exponential function. And as you see, the nuclines on the phase plane diagrams, they are placed like this in this dashed blue one. And the cross-correlation function shows a sharp peak with a smooth exponential decay. And interestingly, we can play with different levels of such an exponential function. So essentially, you can rewrite this exponential function with this limit, 1 plus x over n to the power n. And the higher the n, the closer you are to the exponential function. But the idea here is that you can play with quadratic, cubic, or to the power 10, and the higher the n, the closer you are to the exponential. So for example, n equals 2, we do have the sharp peak, but not so much the exponential decay. Instead, we have a little bump after in some position after the sharp peak, which is different than what we would observe in the pure ADEX model. And if you increase the level of n, this little bump increases and it starts to merge with the sharp peak, the cross-correlation function, until you cannot really distinguish between those two peaks. So this means that when you have nonlinearities in the neuron, you have some additional temporal relationship which may or may not be reflected in the cross-correlation function, which has nothing to do with the sharp peak that we usually observe and we use to infer connectivity, for example. So it means that we have some additional relationship which comes from some intrinsic dynamics that the neuron is developing. And it may or may not be important, but this is the thing that we want to understand. So we do have a proposal for why this is happening. So the idea is that you have two neurons, and a presynaptic neuron is sending a spike that will be perceived to the postsynaptic neuron by postsynaptic current. And this will be perceived after some fixed time delay, tau d, which comes from the synapse, plus some unreliable time delay, which we don't know that a priori. So, but essentially, we have an idea that this unreliable time delay should have something to do with the voltage in which the postsynaptic neuron will be. So if the postsynaptic neuron is on the verge of a spike, this will be close to zero because the postsynaptic neuron will spike right away when it perceives the synapse. And if the voltage is very hyperpolarized, this will take some time to happen until you really observe some influence in the postsynaptic neuron given the presynaptic neuron. So there is some unreliable time window here, which depends on the voltage. And you can try to grasp what this unreliable time delay can do in a cross-correlation functions if you play with artificial spike trains. So that's what we did here. So for example, you can draw, so you can draw Poisson spike trains. So they are uncorrelated and x of t. And you can draw another series where you prescribe neurons here after some tau d of the presynaptic spike, plus some unreliable time delay. And depending on how you use this unreliable time delay, you see that reflection in the cross-correlation function. So for example, if this reliable time delay is 0, you only have the sharp peak, as we would expect. Or if you draw that from an exponential distribution, you see the exponential distribution in the cross-correlation function, or even a Gaussian distribution, or even from two distributions like exponential and a Gaussian, where you get more from the Gaussian, or an exponential and a Gaussian, where you get more from the exponential. So you see how this reliable time delay can cause some jittering on the postsynaptic spike train, and how this is reflected on the as an additional temporal dynamics in the cross-correlation function. It could come with just one additional time, additional dynamics, or two, or even more, depending on this reliable time delay comes from. Okay, so then, I mean, the question would be, what does this have to do with biophysics? And the answer is that when you have neurons that contain ionic currents, those ionic currents play a dynamics intrinsically in the neuron, which are reflected in the same manner in the cross-correlation function, and that you can grasp if you draw a phase plane diagram such as this. So for example, in this neural model of persistent sodium and IH current, we have this type of voltage nucline and the R nucline, which comes from the IH current. And the evolution of the trajectory here, is low on the right side until it will eventually spike in a fast dynamics. So this is very much related with the Canard phenomena. But the important thing here is that when it goes up in this knee, in the voltage nucline, it spends some time on top of this voltage nucline. It somehow lingers around here, which is a time that the trajectory will spend here, and which will be reflected as an additional peak in the cross-correlation function. So which doesn't, it's not really related with the sharp peak, but it's something additional. Now, if you take the same neural model and you play with the parameters in a way that you will bend the right side of this red nucline, this becomes a cubic, and you don't really have this lingering around here. and then you don't see the additional dynamics in the cross-correlation function, so that the trajectory will evolve and will spike right away. You can notice and think that it is understandable that the timescale separation here plays an important role. So, for example, if you increase the timescale separation, this idea that the trajectories will linger around the peak of this quadratic nucline will disappear. So spikes may start to happen right away as you evolve in this red nucline, and then this additional temporal dynamics vanishes, so you don't see that anymore. And you can see that using another view, which would be by looking into the membrane potential density. So with different time scales, this tau r, you see how the voltage is distributed. And we see, for example, for very small tau r, the voltage is very likely that you find the voltage of such a neuron close to that peak of the quadratic nucline. And if that is what is happening, you will see that in the cross-correlation function as additional secondary peak, which is not the same as the first sharp peak. So if you increase tau r, this disappears, and then you don't see the secondary temporal dynamics. And yet another way of seeing that would be to divide the postsynaptic potential of the neuron between two regions. So you could say that you have a region which is a near action potential voltage. So if spikes arrive here in the postsynaptic neuron, this postsynaptic neuron will spike right away because it is on the verge of a spike already. But you also have a subthreshold region. And if the spikes arrive here, they will be processed as a dynamics that will take a while until you perceive in the form of a spike. So for such a simulation, I know that I have in red here, the cross correlation, I have the sharp peak and the secondary temporal dynamics. But what we can do would be to run the same simulation in a way that if spikes arrive at the near action potential voltage area, they will fail. So I only want to observe spikes that will cause influence in the subthreshold level. And if I do that, the first sharp peak completely disappears. So this is the blue line here. So you only have a secondary temporal dynamics. So meaning that this additional dynamics that comes after the sharp peak is something more related to the subthreshold dynamics. And the sharp peak that we observe in the cross-correlation function is very much related to this near action potential voltage. So that the area in which the neuron is already about to spike. And this is also, I mean, most works that they work with cross-correlation functions, it's a common assumption to take synapses that have a strong conductance, and that could also be answered with this experiment, because if a synapse has a very strong conductance, it will cause spikes right away. So you increase this area of near action potential voltage, so you can get very nice sharp peaks in that situation. And this is a little bit different than what we would expect with oscillations. So in the case that you have not only noise, but also a common oscillation added to neurons, you may as well observe additional peaks in the cross-correlation function, but they are a little bit different because they come in both directions. But the issue that I'm addressing here is more related to the intrinsic dynamics of the neuron. which has also something to do with oscillations, and it would be in the case of resonance. So for example, in those simulations here, you see that the amplitude of those oscillations, they increase if you have an intermediate frequency. And because of that, you also get more spikes, which makes the sharp peak to have a higher amplitude. So you see that oscillations play a role, but even here, the intrinsic dynamics of the neurons, they play an additional role, which is something that we think that deserves a further exploration. So that's more or less the message I wanted to convey. So cross-correlation functions, they are useful and informative. They can tell a lot about connections. But what we are trying to say is that you have, we need a proper understanding of how nonlinearities, those that come from ionic currents or time constants, how they are reflected in cross-correlation functions. And a way of getting that would be to evaluate phase plane diagrams, because they are very informative in that respect. And when you see sharp peaks in cross-correlation functions, they usually come from this near action potential voltage, which is when the neuron is already on the verge of a spiking. However, you may have some additional temporal dynamics, which we are disregarding when we don't look into the subthreshold voltage, as we don't look there in the subthreshold voltage of the neuron. So I just want to say thanks to my supervisor, Horacio Hosten, and also some people who we have been discussing and have been helping us a lot, and also the funding acknowledgement, NSF. And that's pretty much what I had to say. So thank you very much.
Thank you very much, Rodrigo. We still have a few minutes left in the session. Does anyone have any questions for Rodrigo?
In particular, if I just wanted to mention that if the panelists have a question, they can do so by unmuting themselves. In the meantime, I would like to ask Rodrigo to elaborate a little bit on what he was mentioning about the canard phenomenon and the timescale separation, because I'm not sure I have fully understood. Yeah, you were in a slide there. Yes, that one. Yeah, or this one. At some point, you mentioned something about the fact that you would increase the timescale separation and or change the timescale separation, and trajectories would spend more or less time, but I have not fully picked up on that. Would you mind reminding us, repeating that?
Yeah, so
I think
they come.
Might have been in the other slides, but I don't know. At the next slide, perhaps. I don't know where you stay.
Okay.
This one, yeah.
Yeah, so the idea, so this model was built on top of the canard phenomena, which is that they come here in a very slow dynamics. They evolve within this slow manifold here, and they have this fast jump, and then you can reset. So the idea is that in this neural model, you have a timescale separation between R and V, and that if you increase this timescale separation, the evolution of this model will become on the R side will be faster, and then it's not really that will come here and slowly go toward this knee and then have a jump, but it can go and will be able to jump right away.
So you increase the timescale separation and it jumps more. That's what you're saying.
Yeah.
It jumps less. Okay. Thank you.